Welcome to the 6th lesson on module 2, which is on analysis of strain. In the last lesson, we had discussed some aspects of strain which occurs due to change in temperature in material, and we had looked into the aspects of lack of fit in a system and the stresses and strain which gets generated thereby. In this particular lesson, we are going to discuss some more aspects of strain analysis, and it is expected once this particular lesson is completed, one should be able to understand the concept of plane strain and strain at a point in different axis system other than reference axis. In general, when we refer the strain, we refer in terms of epsilon x, epsilon y, gamma xy in plane strain. Now, if we orient the axis system other than the rectangular axis system which we consider, then what will be the difference in strain value, that we will look into. One should be able to understand the concept of transformation equations. In fact, for evaluating the strain at different orientation of axis, we need to evolve the equations which we term as transformation equations for evaluating normal and shearing strain, and thereby we will come across the maximum value of the normal strain, which in analogous with the stresses we will term them as principal strain. So, we will look into how to evaluate the values of principal strain and at which orientation these principal strains act at that particular point. Hence, this particular lesson include the recapitulation of previous lesson. In fact, as we have done in the past, we will be discussing the questions which I had posed in the last lesson, and in the process we will recapitulate the aspects which we had looked into in the last class. Evaluation of plane strain at a point on different axis system using transformation equations, and thereby the concept of principal strains and principal angles will generate from these equations of transformation, and we will look into some examples for the evaluation of strains at a point due to the different orientation of axis system from the rectangular axis system. Well, let us look into the answers to the questions which we had posed in the last lesson. The first question was, what is meant by misfit and what are its consequences? Now, you must be remembering that last time I had told that if in any system, if a particular member of a particular length is manufactured or fabricated in such a way that it varies from its original length, then there is a problem of fitting that particular member into the whole structural system, and that leads to some problems. Now, if the system is a determinate one, the geometrical arrangement of the whole structural system will be in problem, but there will not be any stresses or strains generated within that particular system. But if the structural system is indeterminate one, then this length of the member which is not right, which could be longer or shorter, can induce strains and thereby stresses in such members. And thereby, if a member of a structure is fabricated, so please note that if a member of a structure is fabricated from its different from its intended length, then the member will introduce imperfection in the geometry of the structure. Now, this is commonly referred as misfit or lack of fit. Now, for a determinate system, no strains or stresses are produced, except that there will be change in geometry. This aspect I had discussed last time. If we look into, let us say that we have a bar which is supported at this particular point, and we have one member here which is connected at this point, and let us say this is member AB, this is member CD, and if this particular member CD, which is of length L, if this particular length differs, if it is shorter or longer than L, then when we try to fit in this particular member CD into the whole assembly, then there is a possibility that by changing the geometry of this particular system, for example, if CD is longer than L, then this particular member may undergo rotation over here to accommodate the longer length of CD. So, in the process, the geometry of the whole system A, B and CD, which is consisting of these two members, will be different than as expected, because the geometry of this particular system looks like that this bar will no longer be horizontal, but it will be inclined. But in the process, no strains or stresses will be introduced in this particular member. But if we have a system which is indeterminate, then this particular misfit will lead to pre-strain or the pre-stress, which we have discussed in the previous lesson. Now, next question which was posed was, what is the principle of a double acting turnbuckle? Now, if we remember that we introduced the lack of heat by introducing or turning this kind of system which we call as a turnbuckle. Here we have the threaded part in this particular zone, and this particular part which is equivalent to a nut in a nut bolt system. And if this whole assembly is rotated, now we have one threaded part in this particular zone, we have another threaded part in this particular zone. Now, on one side, if the whole assembly is rotated, on right hand side we have a thread, on the left hand side also we have a thread. It is like the whole thing is rotated and there will be movement of the screw towards inside, or if we are rotating on the other side, the screw will move outside. So, thereby there will be change in the length of the whole screw assembly system, either inside or outside. Now, since in one turn it is both the screws are moving, and as we had defined last time that by one turn of a nut or by one turn of this turnbuckle, the movement of the nut for one 360-degree revolution, the movement we call as pitch, which we had defined as P. Now, if we give a turn in a turnbuckle by one full revolution, then both the screws are moving by one pitch. So, thereby there is a total movement of the whole turnbuckle by an amount which is twice P. Now, if we have n number of turns given, so n times twice P will be the total movement of this turnbuckle. So, the deformation delta or the deformation which we are introducing by turning this turnbuckle will be equals to twice Np. And this is the system or the principle on which it works, which can be introduced where we need to introduce the tensile or axial pull, or we like to reduce the length by turning the screws of the turnbuckle. Now, the third question which was posed, which is similar to the second one, is what is the pitch of a bolt and how is it related to the displacement of the nut. Now, let us look into this nut bolt assembly. Now, here this is the nut and this is the bolt assembly. Now, this is the bolt head. Now, when we turn this nut is turned for one full revolution of 360 degree, the knot moves along the length of the threaded part by these two peaks, and this consecutive two peaks in fact is denoted by this letter P, which we call as pitch. So, one movement or one turn of the knot over the full circle moves the knot by a distance P, and this is what is the displacement of the knot by giving a full circle turn along the threaded part of the bolt. Well, having looked into these questions and the answers, now let us look into the strain that we are looking for at a particular point. Now, we are defining the strain with reference to the rectangular axis system as strain in the normal strain in the x direction as epsilon x, normal strain in the y direction as epsilon y, and the normal strain in the z direction as epsilon z. Now, it is similar to the situations as we had in case of stresses. The strain at a particular point in a loaded structure varies. It varies according to the orientation of the axis. If we have a rectangular axis system, then what stress we are expecting? Say for example, we are interested to evaluate the strain at this particular point. Now, at this particular point, the strain which we are referring with reference to the rectangular axis system are epsilon x and epsilon y. Now, if we try to find out the strain at this point at a different orientation of the axis, let us call this as say x1 y1. Now, the strain corresponding to this as epsilon x1 and epsilon y1 will be different from epsilon x and epsilon y, and our objective is to find out the strain along this orientation or in the orientation of the axis, which could be in a general form as theta at any orientation with reference to x and y plane or x and y reference axis, so that we can compute the strain at that particular point at different orientation. Hence, it is necessary to derive the transformation equations. It is necessary to derive the transformation equations for evaluating strain in any direction at that particular point in terms of strains in reference axis system. Now, before we go into the evaluation of transformation equations, let us look into what we really mean by the plane strain condition. Now, as I was indicating that at a particular point, let us say the strains are represented in this particular form. So, this is a small part in a material, and these are the reference axes x, y and z, and the strains which are acting on this in the x direction as epsilon x, epsilon y as the normal strain, and epsilon z as in the z direction. So, we have the strain components which are epsilon x, epsilon y and epsilon z, the normal strains, and the shearing strains are gamma xy, gamma yz and gamma zx. So, these are the 6 strain components which will be acting at this particular point with reference to this rectangular axis system. Now, if we like to represent the strain on a plane which is z plane having x and y axis, the strain that will be existing will be epsilon x, epsilon y and gamma xi, and rest of the strains like epsilon z, gamma yz and gamma xz, they are 0. So, this particular condition of strain we term as plane strain condition. That means, these strains will be acting in this particular plane either in the front part or the back side, which is represented by this x and y axis system, which is basically a z plane. Now, in this plane, if we like to find out the strains corresponding to 3 different directions. Now, if we consider the material in this particular plane only, in the x direction when it is stretching, it is undergoing deformation in this particular direction, and if we say this length as dx, then it will undergo stretching in this particular direction, which is epsilon x dx, epsilon x being the strain, dx being the original length, then the elongation is epsilon x dx. Or it can have stretching in the y direction. This length is dy, so this stretching is epsilon y dy, where epsilon y is the strain in the y direction. In the y direction, strain is epsilon y. Or if we have the shearing strain, which is gamma xy, then the extension is equals to gamma xy times, if we call this depth as dy, gamma xy times dy. So, these are the extensional aspects when we talk in terms of the strain in the plane figures. These are related to the plane strain conditions. Now, let us look into the transformations. We are interested to now evaluate that what will be the strain values at that particular point if we orient the axis with reference to the our rectangular axis system. Say the axis system which is oriented at an angle of theta with reference to x axis. If we are interested to find out the strains, let us look into how do we compute it and what are the corresponding equations which we term generally as transformation equation. Now, x and y, this x and y are the reference rectangular axis, and the strain corresponding to these directions are epsilon x and epsilon y as we are defining, and we are interested to evaluate the strain at this point with reference to the axis system x dashed and y dashed, which is at an angle of theta with reference to x axis. Now, let us consider different cases which are corresponding to the plane strain situation, in which this is the length dx, this is length dy. Now, we consider that the axis x dashed, the x dashed lies along the diagonal of this particular element which we have considered of length dx and dy. Thereby, this diagonal direction is our x dashed axis and perpendicular to that is our y dashed axis. This is the rectangular x and y direction. Now, when this particular element is getting stretched in the x direction, the extension in the x direction is given by this particular length, which is equals to epsilon x times dx. Epsilon x is the strain in the x direction. As we know, strain is equals to delta by dx, delta by the original length. So, original length multiplied by epsilon x will give you the extension delta. So, this is the diagonal, this particular part is the diagonal after it has undergone extension. So, if we are interested to know how much extension this diagonal has undergone with reference to this epsilon x, now this particular length, this particular angle is theta, as we have defined that x dashed axis is lying along the diagonal, and hence x dashed axis is making an angle of theta with x. So, this particular angle is theta. Now, if this is the horizontal distance is epsilon x dx, which is equals to this, then the extension, since this angle is theta, this is theta, and this is being small, this particular one also we are calling as theta. Hence, the extension of the diagonal is horizontal distance times cos theta, which is equals to. So, this particular extension is given as epsilon x dx cos theta. So, this is the extension of the diagonal. Let us call that this particular diagonal is of length ds. So, originally it had a length of ds and it is undergoing an extension which is in terms of epsilon x, which is epsilon x dx cos theta, because of the extension in the x direction. Now, let us look into the situation what happens if it undergoes strain in the y direction and thereby the shearing strain. Now, when this particular element undergoes the strain having again length dx and dy and it is undergoing strain in the y direction. So, this is x axis as we had defined, this is y axis, and as per our definition we said that the diagonal of this particular element is representing the x dashed axis and perpendicular to that is the y dashed axis. So, this is the angle theta, and here in the y direction it is undergoing extension, thereby the extension which is given by this particular length from its original form is equals to epsilon y times dy. So, epsilon y dy is the extension of this element, and because of this stretching the diagonal which was originally of length ds now is getting changed, and this is the changed length of the diagonal, and the extension is given by this particular part of the diagonal which is equals to, now this angle is theta, thereby this particular angle also is theta. So, this is theta. Now, this extension is given by the horizontal extension is given by epsilon y d theta. Hence, the extension which is happening is equals to epsilon y d theta sine component of this, which is equals to this particular extension, and this extension is given by epsilon y d theta sine theta, epsilon y dy sine theta. Epsilon y dy is the vertical extension and the component along the diagonal direction is epsilon y dy sine theta. Now, similarly, the element which is of size dx dy undergoing a shearing strain, and because of shearing strain it is having the shearing strain angle which is gamma xy, and thereby the diagonal which was originally of length ds is undergoing extension which is of this particular form, and thereby the extension of this is given by this particular length, and again this angle is theta as we have defined, hence this is theta, hence this is theta. So, the extension which is this stretch is given by, now this particular extension because of shearing strain is equals to gamma xy times dy, and the extension in the diagonal is equals to is given by gamma xy dy cosine theta. So, we have three extensions of the diagonals obtained now. In the previous case where it was getting stretched in the x direction, we have the extension as epsilon x dx cos theta. In case of stretching in the y direction or strain in the y direction, we have extension of the diagonal as epsilon y dy sin theta, and for the shearing strain the stretching of the diagonal is equals to gamma xy dy cos theta. Hence, the total stretching of the diagonal, if we look into the total stretching of the diagonal, let us call that as delta d. This is given by the extension in the extension due to epsilon x plus extension in the diagonal due to epsilon y plus extension due to gamma xy, and these are given as epsilon x dx cos theta plus epsilon y dy sin theta plus gamma xy dy cos theta. So, these are the three extensions that we have obtained. Now, if we superpose that all three cases because of the plane strain condition, then this is the extension delta d we get for the diagonal one. Hence, the strain in the diagonal direction, which is that of epsilon x dash. Now, epsilon x dash or the strain in the x dash direction is nothing but the strain in the diagonal is equals to the extension of the diagonal divided by its original length, and this is nothing but equals to ds divided by whole of this expression, which is equals to epsilon x times dx by ds times cos theta plus epsilon y dy by ds sin theta plus gamma xy dy by ds cos theta. Now, if we look into the diagram from which we have evaluated this extension, now dx by ds is again cos theta, the dx by ds term is cos theta, dy by ds is nothing but sin theta, and dy by ds again is sin theta. Hence, the whole thing gives us this is equals to epsilon x times cos square theta plus epsilon y times sin square theta plus gamma xy sin theta cos theta. So, epsilon x dashed is the strain in the x direction in terms of the strain epsilon x, epsilon y and gamma xy is given as epsilon x cos square theta plus epsilon y sin square theta plus gamma xy sin theta cos theta. Now, this expression for epsilon x dash further can be simplified. Now, writing cos square theta as in terms of cos 2 theta, let us write epsilon x dashed as equals to epsilon x in place of cos square theta, we write this as half into 1 plus cos 2 theta plus epsilon y times half into 1 minus cos 2 theta plus gamma xy by 2. Now, twice sin theta cos theta will give sin 2 theta. So, this is equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 times cos 2 theta plus gamma xy by 2 sin 2 theta. So, this is the expression for epsilon x dash or the strain in the x dash direction in terms of the strain epsilon x, epsilon y and gamma xy are epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta plus gamma xy by 2 sin 2 theta. Now, similarly, we can compute the value of epsilon y dashed from the expression of epsilon x. Now, since the y dashed axis is at 90 degree with reference to x dashed, this is being 90 degree. So, if we place theta as theta plus 90, we can get the strain in the y dash direction. So, epsilon y dashed we can write as epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 time cos of twice of theta, theta is theta plus 90 which is 180 plus 2 theta plus gamma xy by 2 sin of 180 plus 2 theta. Now, this will give us the value of strain in the y direction, and cos 180 plus 2 theta is minus cos 2 theta, and sin 180 plus 2 theta is minus sin 2 theta. So, the expression for epsilon y epsilon y dashed is equals to then epsilon x plus epsilon y by 2 minus epsilon x minus epsilon y by 2 cos 2 theta minus gamma x y by 2 sin 2 theta. And interestingly, if we note here that if we add this epsilon x dashed plus epsilon y dashed, this gives us the value of the equation as epsilon x plus epsilon y. Now, because other term gets cancelled, hence epsilon x dashed is equals to epsilon y dashed, and if you remember that when we had evaluated the stresses at a point with reference to different orientation of axis, we had seen that the total stress values remain constant. The sigma values of sigma x plus sigma y is equals to sigma x dash plus sigma y dash if it is oriented at different angle, and same thing holds good for the strain as well. The strain with reference to rectangular axis system epsilon x epsilon y is equals to epsilon x dashed plus epsilon y dashed, which are with reference to x dashed and y dashed axis. Well, these are the values which we have just now seen, that epsilon x dashed is equals to epsilon x cos square theta, epsilon y sin square theta, and gamma x y sin theta cos theta, and epsilon x dashed in terms of cos 2 theta and sin 2 theta is given as epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y cos 2 theta by 2 and gamma x y sin 2 theta by 2, and thereby epsilon y dashed is equals to epsilon x sin square theta, epsilon y cos square theta minus gamma x y sin theta cos theta, which eventually comes as epsilon x plus epsilon y by 2 minus epsilon x minus epsilon y times cos 2 theta by 2 minus gamma x y sin 2 theta by 2. So, these are the values of the strain with reference to x dash and the y dash axis. Now, what we need to do, since we said that under plane strain condition we have 3 strain components which are epsilon x, epsilon y and gamma x y. So, under the changed or the oriented axis system with reference to x dashed and y dashed, we will have the strains which are equivalent to the plane strain situation, which are epsilon x dashed, epsilon y dashed and gamma x dashed y dashed, and gamma x dashed y dashed we call as the shearing strain with reference to x dashed y dashed axis. Now, let us evaluate the value of the shearing strain with reference to x dashed y dashed axis. Now, as we know that shearing strain is the angle which is changed from its original 90-degree position. If we have two reference axes which are at 90-degree with each other, the shearing strain causes the change in this 90-degree angle. So, here in this particular case, when we are trying to evaluate the shearing strain gamma x dashed y dashed, let us assume that we had a line OA which was originally lying along this OX dashed. Now, and a line OB originally which was lying on the line OY. Now, because of the shearing strain, they have undergone a change, and let us call this angle as changed angle as alpha and this changed angle as beta. Thereby, the total change which is alpha plus beta from the original 90-degree of OX dash to OY dash, and this change is the shearing strain gamma x dash y dash. So, gamma x dash y dash is equals to alpha plus beta. Now, what we need to do is we corresponding to the 3 changes that we have seen in case of plane strain, corresponding to stretching in the x direction, stretching in the y direction, and because of the shearing strain, that the diagonal which is along the x dashed axis had undergone changes, the diagonal had changes in the angle, and those angles if we join them together we will get the final position of the diagonal. Similarly, the line which is along OY, which is originally we have designated as OB, now under its changed consideration after it has undergone deformation, it has come to position OB. So, there is a change in the angle from OX dash Y OY dash to OA and OB, and these changed angles will give us the value of the shearing strain. Now, to compute those angles, let us go back to the one. Now, in this particular case where we had computed the deformation of the diagonal which was originally ds, and finally it came to this particular position. Now, here we have already seen that this particular extension is epsilon x dx, and this particular stretching of the diagonal was epsilon x dx cos theta. Now, this is the angle which has been changed because of this stretching, and let us call this angle as alpha 1, and then the alpha 1 can be given as this divided by this distance. Now, this particular length is nothing but the extension which is epsilon x dx times sin theta. So, alpha 1 is equals to epsilon x dx sin theta divided by ds. So, epsilon x dx sin theta divided by ds is the angle alpha 1. Alpha 1 is equals to this. Now, please note that this particular angle is undergoing a change in the clockwise direction. Now, let us look into the deformation that we are getting corresponding to the other two cases. Now, in this particular case, the deformation which we have the diagonal, this is the original length ds, and because of the stretching in the y direction, this has taken this particular form, and thereby this is the extension in this particular direction, and let us call this angle change as alpha 2, and this angle change is in an anti-clockwise form, whereas in the previous case it was in the clockwise direction, and the horizontal stretching of this particular element is epsilon y dy as we have seen, and this particular angle is theta. So, this stretching is equals to epsilon y dy cos theta, and that divided by the original length ds will give the value of angle alpha 2. Similarly, when we had the shearing strain, the diagonal was original length of ds, finally it has taken the form which is here, and the extension of this particular length in terms of the shearing strain is gamma xy dy, and again since this angle is theta, this particular value is gamma xy dy sin theta, and that divided by ds will give us the angle alpha 3, which is again in the clockwise direction. So, this is equals to alpha 3. So, now that we have three angles alpha 1, alpha 2, alpha 3, and please note that angle alpha 1 is in the clockwise direction, angle alpha 2 is in anti-clockwise direction, and angle alpha 3 is in a clockwise direction. Now, when we are computing the strain here, which is we have designated as A, and this particular angle is alpha, which is in an anti-clockwise direction. So, alpha is equals to minus alpha 1, which is in a clockwise direction, plus alpha 2, which is anti-clockwise direction, minus alpha 3, which is again in a clockwise direction. So, this net value gives in the anti-clockwise direction, and if we sum up these values of alpha, we get the values as alpha 1 we got as epsilon x dx sin theta. So, this is equals to minus epsilon x dx sin theta divided by ds, plus alpha 2 is epsilon y dy cos theta divided by ds, minus alpha 3 is gamma xy dy sin theta, gamma xy dy sin theta divided by ds. Now, all three together, now again dx by ds as we have seen is cos theta, dy by ds, dx by ds is cos theta, dy by ds is sin theta, and dy by ds again is sin theta. So, this expression turns out to be alpha as equals to minus epsilon x sin theta cos theta plus epsilon y sin theta cos theta minus gamma xy sin square theta. Now, note that this is the value of the angle alpha. Similarly, we will have to compute the value of beta, which is taken by the length OB from its original position OY dash, it has come to this particular position by changing this angle beta. So, alpha plus beta sum will give me the angle gamma x dash y dash. Now, beta can be computed from the expression of alpha itself by placing theta as theta plus 90. Also noting the fact that alpha is computed in an anticlockwise form, whereas beta is in a clockwise direction. So, if we substitute for theta as theta plus 90, now writing down for beta, which is negative of this because in a clockwise direction it is going. So, it is epsilon x sin of theta plus 90 cos of theta plus 90 minus epsilon y sin of theta plus 90 cos of theta plus 90 plus gamma xy sin of theta plus 90 square. Now, the signs have been changed because beta is in a clockwise form and alpha was in an anticlockwise form. Now, this gives us the values as again this as cos theta and sin theta, which is of negative. So, this is minus epsilon x sin theta cos theta, this is again plus epsilon y sin theta cos theta, and this is gamma xy cos square theta. So, if we add this alpha and beta, we get the value of gamma x dash y dash. Gamma x dash y dash is equals to alpha plus beta, and if we add them up, we get epsilon minus twice of epsilon x sin theta cos theta, twice of epsilon y sin theta cos theta, and gamma xy cos square theta minus sin square theta. Gamma xy cos square theta minus sin square theta will give you cos 2 theta, and twice of sin theta cos theta will give you sin 2 theta. Now, if we write down gamma x dash y dash by 2 form, it gives us then gamma x dash y dash as equals to minus of epsilon x minus epsilon y sin 2 theta by 2 plus gamma xy cos 2 theta by 2. So, this is the value of the shearing strain gamma x dash y dash. Now, from this we can compute the values of the principal strain and the angle of principal planes, which is given by twice 2 theta p, and the principal strain as epsilon 1 epsilon 2. This is in similar line to the one which we had computed for the principal stresses and the principal angles. If you remember, when we had computed the stresses, we had evaluated in the same form, and this gives us the value of principal strains and the principal angles. Well, having looked into this, let us look into the problems. One problem which I had posed last time, that the compound bar, which is made out of bronze, aluminum and steel, they are supported between these two supports, and the stress in each of these material is to be computed because of the drop in the temperature by 30 degree centigrade. And here is to be noted that walls do not yield, and the properties of the cross sectional area of the bronze part, cross sectional area of the aluminum part, cross sectional area of the steel parts are given, and corresponding thermal expansion coefficient and the modulus of elasticity values are given. Now, here it is to be noted that if we remove this support, then if we allow this bar to undergo changes because of the change in the temperature, there will be shortening because there is a reduction in the temperature. So, there will be deformation delta which is negative. Now, we will apply a force P to pull this bar and bring it to this particular position, and thereby there will be stresses. So, if we compute that, if we compute the values of the deformation delta, this is equals to 19.0 into 10 to the power minus 6 into 30 is the temperature times the length alpha L alpha t plus 23 into 10 to the power minus 6 is the alpha times t times L plus 11.7 into 10 to the power minus 6 into 30 into 400, and this gives us a shortening of 0.09414 millimeter. And when we pull this by load P, then this elongation minus 0.9414 is to be compensated by the force, which is P times L by A, which is 600 into 200 into 10 to the power 3 plus P times 500 by 1200 into 70 into 10 to the power 3 plus P into 800 divided by 2400 into 83 into 10 to the power 3. This is equals to the values of extension, and from this we get the value of P as equals to 70.8 into 10 to the power 3, so much of Newton, which is tensile, and hence the stresses which we get from this are in the bronze part, sigma bronze is equals to 29.5 MPa, sigma aluminum is equals to 59 MPa, and sigma steel is equals to 118 MPa, which will be P divided by the respective cross sectional area. Now, let us look into the second example problem, which I had said last time, that what will be the stresses that will be produced into this sleeve when there is a quarter turn of the bolt. There is a nut here, and this nut is given a quarter turn, then and the pitch of this bolt is 3 millimeter, which this is the threaded part, this is the threaded part. Now, area of cross section is given, for the copper also is given. This is the steel bolt and these are the copper tube. Now, this is given a turn, and then naturally the copper is under compression, the bolt is under tension. So, we will have to find out that what are the stresses that will be induced in this assembly because of the turning of the nut. Now, since the turn is 1/4, N is equals to 1/4, pitch is 3 millimeter. So, the delta that is equals to n times P, which is equals to 0.75 millimeter, and the compatibility gives that this is the copper sleeve and there is the steel bolt. The compatibility gives that the compression in the copper sleeve is equals to the tensile pull in the steel bolt. So, Ps is equals to Pc. This is the equilibrium criteria, and the compatibility gives that the deformation is same. The deformation delta minus the deformation of the steel, which is PSL by ASES, this is equals to PCLC by ACEC. This is the deformation that is being exerted by the nut minus the extension of the steel should be equals to the compression of the copper tube. And from this, if we substitute the value of delta, which we have already seen here, we get another relation between PS and PC, and also we know PS is equals to PC. From this, PS comes as 80.43 kilonewton, and PS is equals to PC. So, stress in the bolt, sigma bolt, is equals to PS divided by the cross sectional area of the bolt, which is 600 millimeter square, is 133.4 MPa, and the sigma in the copper sleeve, that is equals to this force divided by the cross sectional area, which comes as 66.7 MPa. So, these are the stresses that will be induced into the bolt and the sleeve. So, here we have, please note that we have the equation of equilibrium, which is PS equals to PC, and the compatibility equation is that deformation that is being created by the nut minus the strain because of extension of the bolt, that is equals to the strain that is being induced in the sleeve. So, this criteria along with this gives us the solution for PS and PC. Well, we have another example problem. Please look into this problem. It is for you to look into. In the next lesson we will discuss about it, that the state of plane strain at a point in a body is given by epsilon x, which is 340 into 10 to the power minus 6, epsilon y is equals to 110 into 10 to the power minus 6, gamma xy is 180 into 10 to the power minus 6. What you need to do is that determine the strain components if the axes are oriented at an angle of 30 degree with reference axis in anti-clockwise direction, and also determine the principal strain. Now, this you should be in a position to compute, as we have discussed today, that we have reference axis strain epsilon x epsilon y, and with this reference axis the set of axis is oriented at an angle of 30 degree in an anti-clockwise form. So, you will have to find out the strain at that particular point, since it is a state of plane strain. So, you got to evaluate the strain epsilon x dash, epsilon y dash, and gamma x dash y dash. Also, you will have to find out the principal strains epsilon 1 and epsilon 2. Well, then to summarize, this particular lesson included the concept of plane strain at a point for different orientation of axis system. Like as I said, that with reference to rectangular axis system, we have for plane strain 3 different strains as epsilon x, epsilon y, and gamma xy. Now, at that particular point, for different position of any rectangular axis system, which is oriented at an angle of theta with reference to x and y, we can compute the values of strain in terms of those epsilon x, epsilon y, and gamma xy, and those strains we have termed as plane strain. So, these strains which we evaluate in other reference axis in terms of epsilon x, epsilon y, and gamma xy, we call them as transformation equation. Then the concept of principal strains and principal angles, as we did in case of stresses. Now, from the strains we can compute the values of principal strains and principal angles, we can compute the values of principal strains and the principal angles, which we have done here. Also, we have solved some examples. Of course, these examples which we had posed last time for the evaluation of the strains in a system which is subjected to thermal expansion, which we have solved today. Also, I have set one problem for you in which we got to compute the value of the strain with reference to the rectangular axis system in a axis which is oriented at an angle of 30 degree with x in an anticlockwise form. So, you got to evaluate that, which we will be discussing next time, so that we know how to compute the stresses with reference to that change of orientation of the axis system. Well, now these are the questions posed for you. Now, what is the purpose of transformation equations? Now, from this discussion you will be able to understand that why we really need the transformation equations to be derived, what are the needs for that, and that you should be able to answer. How will you derive the value of maximum normal strain? Now, this particular part, maximum normal strain with reference to the stresses, as we had said, maximum normal stress. So, you should know this particular term, we will be discussing this again. Now, how will you find the value of maximum shear strain at a point for plane strain condition? Now, this also is in similar line with the stresses, as we have computed the values of maximum and the minimum shear when in a loaded structure at a particular point we had evaluated the stresses, and thereby we had computed the principal stresses, we had computed the value of the shearing stresses, and we had computed maximum and minimum shearing stresses. Exactly in the similar line, as we have seen today, we have computed the transformation equations, we have computed the principal strain, we have computed the principal angle. Now, we can compute the maximum shearing strain and the angles for the maximum shearing strain, and in which they will be acting, maximum and minimum shearing strain. So, this is the question, that how will you find the value of maximum shear strain at a point for plane strain condition corresponding to the strains epsilon x, epsilon y and gamma xy. Well, the answers for this will be given in the next class. Thank you for your attention. Welcome to the 7th lesson of module 2, the course on strength of materials. And this module and the lesson is on analysis of strain, part 7.